I welcome you all for this lecture series on deep learning. In this lecture, we'll see equivariant representations in convolution neural networks. First, we should know what is equivariant representation. These equivariant representations are an essential concepts in convolution neural network, that is CNNs, especially when dealing with the visual information such as images. In many real-world cases, objects appear in different positions, scales, or orientations within an image. Because of this variability, neural networks require a mechanism that allow them to detect patterns consistently regardless of where they occur. Equivariant refers to the property of a function in which the transformation applied to the input results in a corresponding transformation in the output. In convolution neural networks, this property is naturally supported by the structure of the convolutional layers, making it possible for the network to understand shapes, edges, and textures even when they appear at different spatial locations. We'll see one by one. First, what is equivariance? You should know equivariance means that when the input undergoes a structured transformation such as shifting or rotating, etc., the output of the function changes in the same structured way. In a simpler terms, the transformation of the output leads to an equivalent transformation of the output. This is particularly relevant in CNNs where the same filter means what? Kernels is applied across the entire image. Because of this shared parameter mechanism, the CNN reacts to feature consistently across positions, meaning that if a pattern appears in a new location, the network identifies it in the same manner as it did elsewhere. This gives CNN the ability to detect patterns independent of the spatial placement. Next, what is main importance of equivariance in CNN? There is importance of equivariance in CNNs. Real-world applications real-world images contain objects that are not fixed to one location in the image frame. For example, a dog. If we take for example, a dog in a photograph could appear near the left, right, top, or bottom of the image. CNNs must recognize the dog no matter where it is located, whether up or downside, no matter it is being where it is located. Equivariance allows CNNs to maintain consistent feature detection across spatial positions, meaning the same features are identified even if they are shifted. This helps the network learn effectively while using fewer parameters. Without equivariance, the network would have to relearn the same feature multiple times in different positions, which would require much larger models and training data. Next, equivariance to translation. This property is very important property. So translation refers to shifting the entire input image along the spatial axis, such as moving it to left, right, up, or down. So this can be done. Equivariance to translation means that if the input image is shifted, the output feature map generated by the convolution also shifts in the same manner. This is a key property of CNNs because most of the real world patterns do not appear in fixed positions. For example, if edge in an image shifts to the right, the location of the detected edge in the feature map will also shift to the right. Thus, convolution allows CNNs to maintain spatial structure in recognition with the tasks. Next, this is the example of the invariance and equivalence. If you are taking this image, this is the cat, and here it is, in this case, it is being reflected or just opposite to this. And whatever the things we are doing it, if you are going for the classification, it will gives us the output as cat. And equivalence, this is invariance. Equivalence means, see here, this is the reflection of this image, segmenting it, it will be getting, you will be getting like this, and also if you are segmenting this, you will be getting this picture. Drawing picture, you will be able to get it. This is what we can call it as invariance and equivalence. Next, the formal definition of the equivalence. This is equivalence in the context of this you can understood. Next, to formal definition of equivalence. Function f of x is equivalent to transformation of g. Transformation could be anything, addition, subtraction, or multiplication, anything. So this is the original image, f of gx equal to g of f of x. X is the input image, g is the transformation, that is shifting or translation. F is the convolution operation, and the meaning is applying transformation before or after convolution produces consistent results. So here it represents what, that is input transformation applied to the input is here transformation of this is g of f of x. This equation states that performing the transformation before or after applying the function leads to results that are equivalent. In the context of CNNs, this means that applying convolution or shifting the input provides the same result as shifting convolution output. This formalization captures the structured consistency of feature detection. Next, parameter setting and equivalence. In convolution layers, the same filter is applied across different regions. This process is known as parameter sharing. Instead of learning separate sets of parameters for every part of the input image, the convolution layer learns one set of filter weights and uses it anywhere and everywhere. This design ensures that similar patterns are detected consistently in different spatial locations. Parameter sharing not only reduces the reduces the total number of parameters in the model, but also directly contribute in the model, but also that is to the equivariance property, since the response of the filter is not tied to a specific position. Next, the example of the translation equivalence. Let G shifts every picture of image I one unit to the right. So to illustrate, consider an image, and the any image you can consider, and translation function G that shifts the image to the right by one pixel. If we first apply the shift and then perform convolution, the resulting feature map will reflect the shifted features. Alternatively, if we first perform convolution on the original image and then shift the resulting feature maps. So we will obtain the same result in the mathematical term. This is expressed as convolution of g of I is equal to g of convolution of v of I. This confirms that convolution preserves the spatial consistency of detected features under translation. Next, feature detection across the image. So if you are taking CNNs detects various visual images elements at different levels of abstractions. In early layers, they detect the simple patterns like edges or corners. In deep layers, they detect more complex structures such as texture, object part, and finally complete the objects. Equivariance ensures that these detections are not restricted to specific regions of the image. Whether a pattern appears in the top left or bottom right of the image, the CNNs requires it in the same way. This robustness makes CNN highly effective in visual recognition tasks. Next, equivalence versus invariance. Equivalence should not be confused with invariance. While equivalence ensures that the output shifts where the input shifts, variance means that the output stays the same even if the input changes. In CNNs, convolution layers are equivalent, while pooling layers such as max pooling introduces the invariance, such as by reducing the spatial sensitivity. Here, pooling that is pooling helps the network become less focused on exact spatial locations and more focused on the presence of features and improving recognition stability under minor shifts. And coming into the summary, Equivariant representations forms the foundation of how CNN process spatial data works. Convolution operations are naturally equivalent to translation due to parameter sharing, enabling CNNs to detect patterns consistently across different image regions. This property allows CNNs to generalize effectively, reduce the number of patterns needed, and supports powerful image recognition capabilities. Understanding these concepts helps explain why CNNs are so successful in computer tasks. So, hope everyone understood about what is equivariance in convolution neural networks. So, you should mainly understand. So, if you are using the image like this, here it is just opposite. And if you are going for the classification, it will give a scat. And similarly here, it is been in the rotated directions. Hope all you can understood this topic. The remaining things we'll discuss in the next lecture. Thank you.